The Indian Ocean has a floor that most people do not know exists. Not the shallow coral reefs, not the warm blue water that appears in photographs. Beneath all of that, the seafloor drops into something else entirely. Trenches so deep that the water pressure at the bottom would collapse a submarine in seconds. Darkness so complete that not a single photon of sunlight has touched those depths in millions of years, and temperatures cold enough to feel like a different planet. The deepest point sits more than 7 kilometers straight down. A human being did not reach it until 2019, and what was found there raised more questions than it answered because something is living at the bottom of the Indian Ocean, in the dark, under that pressure, in conditions that should make life impossible. And the deeper scientists look, the less they understand about what is actually down there or how long it has been living in the silence. In tonight's journey, we're descending into the deepest parts of the Indian Ocean to find out what has been hiding there all along. But before we continue, let me know in the comments if you have any topic suggestions you would like me to cover in future videos. Now, let's descend. A map of the modern world can make the continents seem permanent, as though they have always occupied their familiar positions. Yet the floor of the Indian Ocean tells a quieter story, one written long before any coastline existed. Beneath the water, hidden under layers of sediment and darkness, lie the traces of an ancient rearrangement that unfolded so slowly no living thing could have witnessed it from beginning to end. Around 180 million years ago, there was no Indian Ocean. In its place stood Gondwana, a vast southern supercontinent that joined together lands now known as Africa, South America, India, Australia, Antarctica, and Madagascar. Mountains crossed regions that would one day be separated by entire oceans. Rivers flowed across landscapes that no longer share a horizon. Forests spread over ground that would eventually drift thousands of kilometers apart. Gondwana itself formed only part of a greater world called Pangaea, a supercontinent so immense that it gathered most of Earth's land into a single connected mass. To the north lay Laurasia. Between these giant continental realms stretched the Tethys Sea, a warm tropical ocean whose waters occupied the space where future mountains and future oceans would emerge. For millions of years, the Tethys drifted beneath changing skies, carrying sediments, marine life, and the slow movements of the planet's crust. Though it vanished long ago, its legacy remains woven into the geography of the modern world. The transformation began almost imperceptibly. Deep beneath Gondwana, forces within Earth's mantle continued their restless circulation. Heat rose, rocks shifted, stress accumulated across the crust. Around 150 million years ago, fractures appeared. What had once been joined began to separate. Madagascar and India slowly pulled away from Africa and Antarctica, creating a narrow opening where seawater entered and a young ocean started to form. At first, the movement was measured in millimeters each year, a pace almost beyond imagination. Yet geological time rewards patience. Century after century, millennium after millennium, the gap widened. New oceanic crust emerged between the drifting fragments. The basin that would become the Indian Ocean gradually expanded, carrying entire continents away from their former neighbors. Then India began an extraordinary journey. Around 80 million years ago, its motion accelerated dramatically. Geological evidence suggests it was pulled northward by a rare arrangement of subduction zones operating simultaneously. Oceanic crust disappeared beneath surrounding plates, drawing the Indian landmass forward at one of the fastest tectonic speeds known in Earth's history. For roughly 30 million years, India crossed the widening ocean like a colossal stone raft, moving through tropical seas toward a destination not yet visible on any horizon. The voyage ended in collision. Around 50 million years ago, India reached Eurasia. Neither continent could easily sink beneath the other. Instead, the crust compressed, folded, and thickened. Layers of rock that had once rested beneath ancient seas were pushed upward toward the sky. The result was the Himalayas, the tallest mountain range on Earth, rising from the final closure of much of the Tethys Sea and preserving within their rocks fragments of vanished oceans. The Indian Ocean still carries the imprint of that immense history. Its floor is crossed by an inverted Y-shaped network of spreading ridges: the Central Indian Ridge, the Southeast Indian Ridge, and the Southwest Indian Ridge. These submerged mountain chains continue to create new seafloor even now, slowly widening parts of the basin through the same forces that began breaking Gondwana apart. Nowhere else on Earth do three major mid-ocean ridges meet in quite the same way. The deepest trenches, the volcanic ridges, the unusual habitats, and the remarkable creatures that inhabit them all trace their origins back to this broken world, a world whose fragments never truly stopped moving. The shape of the Java Trench cannot be seen from the sea above. Ships pass over it without any hint that beneath their hulls the seafloor bends downward into the deepest place in the entire Indian Ocean. Hidden beneath thousands of meters of water, it curves along the southern and western margins of Sumatra and Java, tracing a vast arc across the ocean floor for roughly 3,200 kilometers. From above, it is invisible. From below, it is one of the most powerful geological boundaries on Earth. At its deepest verified point, the trench descends to 7,192 meters. If the tallest mountain in Scotland were lowered into this depression, its summit would remain far below the surface. Here, the Indian Ocean reaches a realm found nowhere else within its basin, the hadal zone, the deepest ecological domain on the planet. Every other deep feature in the Indian Ocean stops short of this threshold. Only the Java Trench continues downward into that darker and more isolated world. Its existence is the result of an immense geological encounter that has been unfolding for millions of years. Along the trench, the Indo-Australian plate slowly slides beneath the Sunda plate and the Burma microplate, disappearing into Earth's interior. The motion is measured in centimeters each year, yet the cumulative force is staggering. Entire sections of oceanic crust are drawn downward, recycled into the mantle, while the overriding plate is compressed, fractured, and reshaped above. Nothing about this process is truly still. Even when the seafloor appears motionless, the collision continues beneath it. Rocks bend, stress accumulates, faults lock together and hold for decades or centuries before shifting again. The trench is less a fixed location than an ongoing event, a place where the architecture of the planet remains under construction. On the 26th of December 2004, that hidden tension was released in a matter of minutes. A rupture extending for more than 1,300 kilometers tore through the boundary. The earthquake reached a magnitude of 9.1, making it one of the largest ever recorded by scientific instruments. Far below the ocean surface, sections of seafloor were suddenly displaced. Water above them was lifted and pushed outward, setting immense waves into motion across the Indian Ocean basin. The tsunami that followed crossed entire oceans. Coastlines thousands of kilometers apart became connected by the same pulse of energy. Approximately 230,000 people lost their lives across 14 countries, while nearly 1,700,000 more were displaced. The event remains among the deadliest natural disasters in recorded history, and its origin lay along the same trench that now shelters some of the least known ecosystems on Earth. Yet despite its significance, the deepest reaches of the Java Trench remained largely untouched by direct exploration. For much of the 20th century, knowledge of the trench came from sonar readings, sediment samples, and occasional biological collections. Scientists lowered benthic trawls into the darkness, dragging heavy nets across the seafloor in hopes of recovering fragments of life from depths they could not observe directly. The method provided glimpses, but only glimpses. Creatures arrived damaged, incomplete, or detached from the environments they inhabited. The last substantial biological sampling of the deepest regions occurred during the 1950s. After that, the trench slipped back into obscurity. Decades passed, technologies advanced, satellites circled the planet, human beings walked on the moon and built laboratories in orbit. Meanwhile, the deepest habitat in the Indian Ocean remained almost entirely unseen. For more than 60 years, the hadal depths of the Java Trench waited in silence beneath the shifting plates, beneath the storms and shipping lanes above, continuing their slow geological work while generation after generation passed overhead without returning. In the spring of 2019, a research vessel drifted above a place that had existed for millions of years without ever receiving a human visitor. Beneath its hull lay the deepest point of the Indian Ocean, a location known through measurements and maps, yet untouched by direct observation. The long silence surrounding that depth was about to end. The expedition responsible was known as the Five Deeps Expedition, an ambitious effort to reach the deepest point in each of Earth's oceans. Leading the mission was Victor Vescovo, a former naval intelligence officer whose fascination with exploration had carried him from mountain summits to polar landscapes and now into the deepest reaches of the sea. For this undertaking, he commissioned a remarkable vessel, the DSV Limiting Factor, a crude submersible built by Triton submarines and designed to withstand the immense pressures found at full ocean depth. Unlike earlier deep diving craft that could only make a handful of descents, this vehicle was engineered to travel repeatedly into places where the weight of the ocean pressed down with extraordinary force. On the day of the dive, the sea above the trench was warm beneath tropical skies. The contrast with earlier stages of the expedition was striking. Only months before, similar preparations had taken place in waters edged by Antarctic ice. Here the atmosphere felt entirely different, yet the destination below belonged to the same hidden realm shared by all of Earth's deepest oceans. Vescovo entered the submersible alone. As support crews completed their final checks, the vehicle slipped beneath the surface and began its descent. The ocean above gradually faded from view. Layers of water passed in slow succession. The bright world of waves and sunlight receded overhead, becoming increasingly distant as the submersible continued downward. Hours passed. Within the first few hundred meters, daylight weakened. Far below the reach of the sun, darkness settled across the surrounding water. The only illumination came from the vessel itself, and from occasional living sparks in the distance. Tiny flashes appeared and vanished beyond the viewport, brief signals produced by drifting organisms carrying their own light through the depths. The descent became a quiet journey through a region that had never known morning or evening. Eventually, the instruments confirmed arrival. At a depth of 7,192 meters, the DSV Limiting Factor touched the floor of the Java Trench. For the first time in history, a human being sat at the deepest point of the Indian Ocean. Around the submersible stretched a landscape that had remained unseen despite lying on a planet explored for centuries. The cameras began recording immediately. Expectations before the dive had often leaned toward simplicity, a broad plain of sediment with little activity. What appeared on the monitors suggested something quite different. Movement emerged across the seafloor. Small organisms occupied the sediment. Creatures drifted above it. The deepest habitat in the Indian Ocean was not empty, it was inhabited. The crude descent formed only part of a larger scientific effort. Throughout the expedition, autonomous landers were deployed into the trench. These robotic platforms carried cameras, sensors, and baited equipment designed to operate independently on the seafloor. Descending separately from the submersible, they observed multiple locations and gathered information from environments that no diver could visit simultaneously. Together, they created a broader portrait of the trench than a single vehicle could provide. Among those involved was Dr. Alan Jameson of Newcastle University, the expedition's chief scientist and one of the leading researchers of hadal ecosystems. On a separate dive, he descended to 7,180 meters, establishing the deepest dive ever completed by a British citizen. Across 5 days of work, the expedition documented communities that had remained unseen for more than 6 decades and identified at least 4 species previously unknown to science, adding new inhabitants to the growing story of life in the deepest reaches of the Indian Ocean. Not every discovery announces itself with size, speed, or strength. Sometimes a scientific mystery arrives quietly, crossing a camera frame for only a few moments before disappearing back into the darkness from which it emerged. Among the many hours of footage gathered from the floor of the Java Trench, one such visitor appeared, and for the researchers watching the recordings, it became impossible to forget. The creature drifted slowly through the water column, suspended above the seafloor with an almost weightless grace. Its body was translucent and softly wrinkled, neither fish nor jellyfish, neither familiar nor easily classified at first glance. A bulbous form tapered into a long, slender stalk that trailed behind it. In the dim illumination of the lander's lights, it resembled an object entirely out of place, something fragile and accidental that had wandered into one of the most extreme environments on Earth. Yet nothing at that depth is accidental. The animal was eventually identified as a stalked ascidian, a member of the tunicates. Sea squirts, as tunicates are commonly known, rarely capture much public attention. Most live attached to rocks or other surfaces, quietly filtering seawater for nourishment. Their appearance gives little hint of their deeper biological significance. During their earliest life stage, tunicates possess a structure known as a notochord, an ancestral feature shared with the lineage that eventually produced all vertebrates. In an unexpected way, this strange drifting organism belonged to a branch of the family tree that also includes fish, birds, mammals, and human beings. Even among tunicates, however, this individual appeared unusual. Its shape did not comfortably match previously documented species. Its proportions were distinctive. Its location was extraordinary. Researchers studying the footage found themselves comparing images and records, searching for familiar characteristics, yet the animal resisted easy placement. The deeper they looked, the more it seemed to stand apart. Dr. Alan Jameson later reflected on the encounter as one of the rare moments in exploration when observation briefly outruns explanation. Scientific work often proceeds through careful accumulation, one detail building upon another. Yet occasionally an organism appears that interrupts that process, creating a pause before understanding can catch up. This drifting ascidian became one of those moments. Its home lay at a depth of roughly 7,000 meters. Here the pressure exceeds 700 atmospheres, an invisible weight pressing from every direction at once. Conditions that seem normal at the surface no longer apply. Biological structures must function under compression so immense that materials familiar to human engineering can deform or fail. Every cell, every membrane, Every molecular process inside the animal operates within a physical reality profoundly different from the one experienced on land. Despite those conditions, the stalked ascidian survives through a remarkably simple lifestyle. Like its relatives in shallower waters, it feeds by filtering tiny organic particles from the surrounding sea. Water passes through its body, microscopic food is extracted, nutrients are gathered from a realm where resources arrive only sparingly. The hadal environment offers no abundance. Food drifts downward slowly from ecosystems thousands of meters above, and what finally reaches the trench floor is only a small fraction of what once existed near the surface. That such a creature evolved to thrive there speaks to the patience of evolution itself. Over immense spans of time, life has repeatedly discovered ways to occupy places that seem impossibly hostile. The stalked ascidian represents one of those solutions, shaped by pressures and limitations found almost nowhere else on Earth. As images of the organism spread beyond the expedition, it became widely known as the living balloon on a string. The nickname captured its appearance but not its mystery. Years after its discovery, the animal remains formally undescribed. It has not received an official scientific name. Its exact place within the catalogue of life is still being examined, preserved for now in a handful of recordings and observations, drifting gently through the deepest waters of the Indian Ocean. Some animals seem shaped less by ancestry than by the places they inhabit. Across vast distances, separated by entire oceans and isolated from one another for immense spans of time, evolution occasionally arrives at the same answer more than once. Deep within the trenches of the world, one such answer appears again and again, a small fish whose form has become almost synonymous with life at the edge of the possible. As the cameras of the DSV limiting factor surveyed the floor of the Java Trench, they recorded a delicate figure moving above the sediment. It was not large. Compared with many familiar fish, it would have seemed almost fragile. Yet here, in one of the most extreme environments on Earth, it occupied the role of a successful predator. This was a hadal snailfish, a member of the family Leporidae, and one of the deepest living vertebrates ever observed. Its appearance carried none of the features often associated with strength. The body was pale and translucent, allowing hints of its internal structures to show through the skin. There were no scales reflecting light, no armor, and no rigid profile. Instead, the fish possessed a softness that seemed almost improbable. Individuals of this group rarely exceed a few dozen centimeters in length, yet their modest size conceals an extraordinary degree of specialization. Every aspect of the snailfish reflects the demands of its environment. Unlike many shallow water fish, it lacks a swim bladder. Such gas-filled structures become increasingly difficult to maintain under immense pressure. Its skeleton contains a greater proportion of cartilage and less heavily mineralized bone. The muscles are loosely organized and rich in water. What might appear delicate from a human perspective is in fact a sophisticated response to conditions that punish rigidity. At hadal depths, flexibility becomes an advantage. Soft tissues endure where harder structures would struggle. The fish observed in the Java Trench shared this familiar blueprint, one that researchers have encountered in deep trenches throughout the world. Similar snailfish have been documented in the Pacific, the Atlantic, the Southern Ocean, and now the Indian Ocean. Again and again, wherever scientists have managed to reach the deepest depressions of the seafloor, some variation of this animal appears. Dr. Alan Jameson often remarked upon that consistency during his explorations of hadal environments. Trench after trench revealed similar forms, as though distant ecosystems, separated by thousands of kilometers, had independently settled upon the same solution. The pattern is striking because these habitats are not connected in any obvious way. Deep trenches function almost like isolated valleys, separated by enormous stretches of seafloor and barriers that would challenge many species. Whether the Java Trench population represents a distinct species remains uncertain. Externally, it closely resembles snailfish found elsewhere, yet appearances can be deceptive. Genetic differences sometimes accumulate silently over millions of years, hidden beneath outward similarities. Researchers continue to examine specimens and observations, searching for clues that might reveal how closely these distant populations are related. Regardless of their exact classification, snailfish occupy a central role within hadal ecosystems. They are the dominant vertebrate predators of the trench floor. Their principal prey consists of amphipods, small crustaceans that gather wherever organic material settles from above. These scavengers transform scarce resources into living biomass, and the snailfish, in turn, convert that abundance into movement and predation. The footage from the Java Trench showed none of the urgency often associated with hunting. The fish moved with deliberate patience, gliding low over the sediment. Every motion appeared measured. There was little reason for haste in an environment governed by scarcity and efficiency. Energy is precious at these depths, and successful animals spend it carefully. Around the snailfish stretched a landscape largely untouched by cycles familiar to the surface world. There was no sunrise, no changing weather, no seasonal bloom. Time expressed itself differently here. Fine organic particles settled slowly from distant waters above, providing a steady but limited supply of nourishment. Within that ancient rhythm, the snailfish continued its quiet search across the trench floor, a small, translucent hunter perfectly at home in one of the most remote habitats on the planet. Pressure is invisible. It has no color, no scent, and no sound of its own. Yet in the deepest part of the Indian Ocean, it is the defining presence, more constant than rock, more influential than temperature, shaping every living thing from the inside out. At the floor of the Java Trench, the ocean presses downward with such force that the environment can no longer be understood through ordinary experience. The rules governing life near the surface begin to dissolve long before these depths are reached. At approximately 7,192 meters, the pressure exceeds 718 atmospheres. Every square centimeter bears a burden of more than 718 kilograms. Comparisons help illustrate the scale, though none fully capture it. A standard scuba tank contains air compressed to around 200 atmospheres. The maximum operating depths of military submarines remain closely guarded, yet estimates generally place them somewhere between a few hundred meters and perhaps 500 meters. The floor of the Java Trench lies far beyond those limits, in a region where engineering and biology confront conditions unlike those found almost anywhere else on Earth. For most forms of life, such pressure is not merely uncomfortable, it is destructive. Proteins, the molecular machines responsible for countless biological tasks, depend upon delicate three-dimensional shapes. Under extreme compression, those shapes begin to distort. Enzymes lose their ability to function properly. Cell membranes, normally flexible and fluid, become increasingly rigid. The chemistry required for life gradually falters. An organism adapted to shallow water would not survive long in such an environment. Yet the trench is not empty. Life persists because some organisms have undergone a transformation so profound that pressure itself has become part of their biological identity. Scientists refer to these organisms as piezophiles, from a Greek word, associated with pressure. For them, immense compression is not an obstacle to overcome, but a condition around which every aspect of their existence has evolved. Among the most remarkable are certain deep-sea microorganisms. In laboratories, researchers have isolated bacteria from ocean trenches that grow best under pressures ranging from 700 to 1,000 atmospheres. Some species perform poorly when pressure is reduced. Others struggle to survive outside their native conditions altogether. One such organism, Colwellia hadaliensis, recovered from the Puerto Rico Trench at more than 7,400 meters, cannot reproduce below roughly 370 atmospheres. The environment humans consider normal is, for this microbe, profoundly abnormal. The same principle extends upward through the food web. The fish inhabiting hadal ecosystems possess biochemistry subtly tuned to the demands of compression. Their enzymes do not merely tolerate pressure. In many cases, they function more efficiently because of it. Studies examining lactate dehydrogenase, an enzyme involved in cellular energy production, reveal a striking pattern in hadal snailfish. As pressure increases, enzyme activity can become stronger rather than weaker, the opposite of what occurs in many shallow water species. Even the membranes surrounding their cells reflect this adaptation. To remain flexible under constant compression, piezophilic organisms incorporate greater proportions of unsaturated fatty acids into their membranes. These molecules help preserve fluidity where ordinary biological materials might stiffen. At the microscopic scale, life adjusts itself with extraordinary precision, modifying the chemistry of every boundary and every reaction. Such adaptations reveal an important truth about the deepest reaches of the ocean. The animals and microorganisms living there are not enduring hostile conditions in the way a visitor might endure a storm. They are products of those conditions. Generation after generation has been shaped by immense pressure until the distinction between organism and environment becomes difficult to separate. The trench does not merely provide a setting for life, it participates in its construction. Over millions of years, compression has acted as a patient sculptor, refining proteins, membranes, enzymes, and cells into forms capable of functioning beneath a weight that would destroy most familiar creatures. What appears impossible from the surface becomes ordinary at depth, and within that unseen realm, life continues according to a different set of molecular expectations, written not by sunlight or weather, but by the steady force of the ocean itself. Most maps portray the deepest point of a trench as a destination, a single location marked by a number. Yet the floor of the Java Trench is not merely a lowest point on a chart. It is part of a larger landscape, one with slopes, ridges, exposed rock, and hidden transitions that can transform within the span of a few hundred meters. During the historic dives into the trench, one of the most revealing discoveries emerged not from remaining at the bottom, but from moving away from it. After reaching the deepest part of the trench, the DSV limiting factor began a carefully planned scientific transect. Rather than remaining stationary on the sediment, the submersible traveled upward along a steep escarpment rising from the trench axis. The route carried it across a natural boundary where geology and biology changed together, revealing that even at hadal depths, the seafloor is far from uniform. The escarpment rose approximately 150 meters above the trench floor. In human terms, it was comparable to a towering cliff. Its face consisted of exposed rock extending upward toward a plateau situated at roughly 7,050 meters depth. While the difference in elevation might appear modest compared with the overall depth of the trench, the transition produced a remarkable change in habitat. At the base of the escarpment lay a broad expanse of fine sediment. Here, holothurians, more commonly known as sea cucumbers, occupied much of the visible landscape. These animals moved slowly across the soft substrate, feeding upon organic material embedded within the mud. The environment was relatively uniform, shaped by the gradual accumulation of particles settling from the waters above. As the submersible climbed the rock face, that uniformity began to disappear. The cameras revealed hard surfaces where sediment could no longer accumulate in thick layers. Exposed bedrock created entirely different opportunities for life. Organisms that required stable attachment points appeared on the cliff face, replacing communities adapted to soft ground. The shift occurred over a surprisingly short distance, illustrating how even subtle changes in terrain can reshape an ecosystem. Among the most prominent inhabitants were sea anemones. Their bodies extended from the rock like delicate living flowers, anchored securely to the vertical surfaces. At least 2 species were observed during the ascent. Nearby, sea stars occupied sections of the escarpment, adding another layer of complexity to the community. These animals depended upon conditions unavailable on the muddy trench floor below. The rock itself created a habitat every bit as important as depth or pressure. The cliff face also displayed evidence of constant geological activity, sediment collected within cracks, ledges, and sheltered recesses. In some locations, fine material had accumulated in narrow channels before spilling downward under the influence of gravity. These sediment chutes resembled miniature underwater landslides, carrying particles from higher elevations toward the trench floor. Though slow and subtle, they revealed a landscape in motion rather than a static geological monument. At the base of steeper sections, the submersible encountered talus deposits, scattered accumulations of broken rock that had detached from the escarpment above. These debris fields indicated that portions of the cliff occasionally fractured and collapsed. Compression generated by converging tectonic plates continues to shape the region, while gravity steadily pulls loosened material downward. The escarpment is therefore not a permanent structure frozen in time. It is continuously being modified by the same forces that created the trench itself. Geologists identify this region as part of the forearc, a zone caught between the trench axis and the overriding tectonic plate. The exposed rock serves as a record of ancient collisions, preserving evidence of the long interaction between the Indo-Australian plate and the Eurasian margin. Each layer reflects stages in a process that has unfolded over millions of years beneath the ocean. What made the transect especially valuable was the amount of information gathered in only a few hours. Earlier generations of researchers relied largely on trawls dragged across the seafloor, methods that often obscured the relationship between organisms and their surroundings. By directly observing the escarpment, scientists witnessed a mosaic of habitats existing side by side. A single ascent revealed ecological variety that decades of indirect sampling had struggled to capture, transforming a simple climb up a cliff into one of the most illuminating journeys ever made within the deepest part of the Indian Ocean. From a distance, the deepest reaches of the ocean can appear deceptively simple. Depth charts often reduce them to contours and numbers, smooth depressions descending into darkness. Yet when scientists finally began observing the Java Trench directly, a different picture emerged. What seemed at first like a single habitat revealed itself as a collection of separate worlds, each shaped by its own geology and occupied by its own community of organisms. The realization became clear through detailed analysis of observations gathered during the recent expeditions. In a scientific study published in 2022, researchers, including Alan Jameson, Thomas Stewart, Tom Weston, and Victor Vescovo, described at least 6 distinct habitats within the hadal zone of the trench. The finding transformed understanding of a place once assumed to be comparatively uniform. At the lowest elevations lay the trench axis, a broad region of fine sediment occupying the deepest portions of the depression. Here the seafloor stretched outward in gentle contours, covered by mud accumulated over immense spans of time. Holothurians moved across this landscape, processing the organic material embedded within the sediment. Their presence gave the habitat a quiet sense of continuity, life sustained by resources arriving gradually from distant waters far above. Beyond the trench axis rose the steep escarpment, where exposed rock interrupted the softer terrain. Hard surfaces created opportunities unavailable elsewhere. Sea anemones anchored themselves to the cliff face, while sea stars occupied ledges and protrusions. Organisms adapted to attachment flourished where sediment-dwelling species could not. The transition was not gradual but immediate, demonstrating how strongly the structure of the seafloor influences the distribution of life. Within the escarpment itself existed another environment entirely. Crevices and sheltered depressions trapped pockets of sediment that accumulated in protected locations. These small deposits functioned almost like isolated islands, supporting their own assemblages of organisms. A few meters could separate one community from another, each responding to subtle differences in stability, sediment composition, and available resources. Other sections of the cliff displayed sediment chutes, narrow pathways where loose material migrated downslope. Fine particles gathered and occasionally flowed through these channels under the pull of gravity. Conditions here remained less predictable than in surrounding habitats. Organisms living within such zones existed in landscapes subject to continual rearrangement, adapting to surfaces that could slowly shift over time. At the foot of steeper slopes, talus fields spread across the trench floor. These accumulations of fractured rock originated from structural failures higher on the escarpment. Blocks and fragments detached from the cliff and settled below, creating habitats characterized by irregular surfaces and complex shelter opportunities. The geology itself became an architect of ecological diversity, constructing environments through the gradual breakdown of stone. Above the escarpment lay a plateau at roughly 7,050 meters depth. Though separated from the trench floor by only a modest vertical distance, the plateau possessed a distinct sediment composition and supported different biological communities. The discovery reinforced an increasingly important lesson from deep ocean exploration. Depth alone does not determine the nature of a habitat. Structure, stability, substrate, and geological history all contribute to the character of a place. As researchers examined the results, the scale of biodiversity proved especially striking. Organisms representing 10 phyla, 21 classes, 34 orders, and 55 families were documented within the surveyed region. Many records extended the known geographic ranges of species or established new depth records. What had once been imagined as a sparsely populated environment revealed an unexpectedly rich tapestry of life. Among the most intriguing observations were patches of bacterial growth attached to exposed rock surfaces. Researchers documented 36 separate occurrences, appearing as orange, yellow, and white mats spread across sections of the escarpment. Their presence suggested the possibility of chemosynthetic activity, biological processes powered not by sunlight or drifting organic matter, but by chemical reactions occurring within the surrounding geology. If further study confirms this interpretation, parts of the Java Trench may support ecosystems, drawing energy directly from the rocks themselves. In a realm long associated with scarcity, these bacterial communities hint at an additional source of sustenance woven into the structure of the trench. The deepest region of the Indian Ocean thus becomes more than a single habitat. It becomes a mosaic of interconnected worlds, each revealing a different way for life to persist beneath the immense weight of the sea. Names can linger long after understanding changes. Across maps, scientific reports, and popular descriptions, one deep feature of the Indian Ocean spent decades carrying a title that seemed perfectly reasonable. It was called the Diamantina Trench, a name repeated so often that it became accepted almost without question. Yet beneath the label lay a geological story entirely different from the one the word trench suggests. Far to the west of Australia, roughly 1,300 kilometers from the coastline, the seafloor descends into a vast region known as the Diamantina Fracture Zone. For many years, it was frequently listed among the deepest places in the Indian Ocean, and in that respect, the reputation was deserved. What proved less accurate was the classification itself. Despite its depth, the Diamantina is not a trench in the geological sense. True oceanic trenches form where tectonic plates converge and one plate descends beneath another. They are products of subduction, the same immense process responsible for creating the deepest scar in the Indian Ocean farther to the north. The Diamantina emerged through an entirely different mechanism. Rather than being squeezed together, the crust in this region was pulled apart. As tectonic plates moved away from one another, the seafloor fractured and stretched, creating a complex landscape of ridges, valleys, escarpments, and deep depressions. The distinction may seem subtle, but it reveals two very different chapters in Earth's history. One landscape records collision, the other records separation. Within the fracture zone lies its deepest known point, the Dordrecht Deep. Measurements place this depression between approximately 7,019 and 7,100 meters below the ocean surface. During the Five Deeps expedition in 2019, researchers surveyed the region alongside their work in the Java Trench. The results confirmed that the Java Trench remains the deepest location in the Indian Ocean, yet the Dordrecht Deep still ranks among the ocean basin's most profound features. Despite that significance, no human being had ever descended into the Dordrecht Deep. The feature remained known primarily through sonar measurements and remote observations. It existed on charts and maps, but not within direct human experience. That changed in January of 2023. The Chinese submersible Fenduje reached the Dordrecht Deep, completing the first crewed descent into this remote environment. The dive marked a new chapter in the exploration of the southeastern Indian Ocean, transforming a location previously understood through instruments into a place observed firsthand. The expedition gathered an extensive collection of scientific data. High-resolution multi-beam sonar surveys mapped roughly 3,000 nautical miles of seafloor. Researchers also conducted 28 scientific dives, recording video observations and collecting sediment samples through push-core techniques. Each descent added detail to a region that had remained largely unexplored despite its extraordinary depth. The broader fracture zone extends for approximately 1,900 kilometers, stretching from the 90 East Ridge toward the Natural East Plateau off southwestern Australia. It was first identified during surveys in the 1950s and later named after the Diamantina River, linking one of the ocean's deepest geological features to a river flowing across the Australian continent. As mapping technology improved, the fracture zone revealed increasing complexity. Rather than a single depression, it consists of an intricate arrangement of geological structures shaped by ancient tectonic forces. Ridges rise from the seafloor. Deep valleys separate elevated blocks of crust. Escarpments form dramatic boundaries between regions of differing elevation. Among these features, the Diamantina Escarpment stands out. Sonar mapping shows a drop exceeding 5,100 meters, a vast underwater wall descending through darkness on a scale difficult to imagine. Such structures are reminders that the seafloor is not a flat plain hidden beneath the ocean, but a landscape as varied and dramatic as any found on land. The Diamantina Fracture Zone therefore occupies a unique place within the Indian Ocean. Though often mistaken for a trench, it tells a different geological story, one written not through collision, but through separation, preserving within its fractured depths the record of continents slowly pulling apart across immense spans of time. Long before the deepest valleys of the Diamantina existed, the rocks beneath them belonged to a very different world. They were part of a continuous landscape tied to ancient continents, connected within the vast southern supercontinent whose slow disassembly reshaped the planet. The fracture zone visible today is not the result of collision or burial beneath another plate. It is the preserved signature of a separation that unfolded across millions of years, leaving behind a geological record written in stretched crust and broken stone. The origins of the Diamantina Fracture Zone reach back to the opening of the Indian Ocean itself. As Gondwana gradually fragmented, Australia and Antarctica began drifting apart. The process was neither smooth nor symmetrical. Beneath the expanding ocean basin, new seafloor formed along spreading ridges, but the ridges did not remain perfectly aligned. Instead, they were offset by transformed faults, immense fractures where sections of crust slid sideways relative to one another. These faults cut across the growing sea floor like seams in a slowly widening fabric. Over time, they produced a pattern of ridges and valleys extending across the southeastern Indian Ocean. The result was a landscape defined by elongation rather than compression, shaped not by plates converging, but by plates moving away from each other. The Diamantina Fracture Zone emerged from this process, preserving the geometry of separation within its structure. Today, the region occupies a remote section of the ocean basin, south of the Wharton Basin and the Perth Basin, and southwest of the Naturaliste Plateau. Though hidden beneath thousands of meters of water, its architecture remains visible through modern mapping technologies. Long parallel ridges alternate with deep depressions, tracing the ancient pathways of tectonic motion. Each valley and escarpment records a chapter in the gradual opening of an ocean. This history sets the Diamantina apart from the deepest reaches of the Java Trench. Both descend into remarkable depths, yet they owe their existence to fundamentally different forces. The Java Trench is an active boundary where one tectonic plate continues to descend beneath another. Earthquakes, deformation, and ongoing tectonic activity shape the region. The Diamantina, by contrast, resembles a geological fossil. The dramatic movements that created it belong largely to the distant past. What remains is the preserved scar of a former tectonic process rather than a boundary currently consuming oceanic crust. That difference extends beyond geology and into biology. The physical history of a deep environment influences the resources available to its inhabitants. Active subduction zones can generate conditions that support unusual ecosystems. Geological instability may trigger sediment movements that redistribute nutrients. In some locations, chemical reactions associated with tectonic activity, provide alternative sources of energy for microbial communities. The Diamantina offers a quieter setting. Here, the dominant rhythm is not driven by active convergence, but by long-established stability. The water remains cold and dark, yet the geological background is comparatively subdued. Without the same degree of tectonic activity, life depends more heavily upon material arriving from the upper ocean. Organic particles descend through the water column and settle onto the seafloor, forming the primary foundation for many biological communities. For scientists attempting to understand the Dordrecht Deep, this distinction is important. Organisms inhabiting the fracture zone are expected to differ from those occupying active hadal trenches. Their environment has been shaped by a separate geological history, and over time, that history influences which adaptations prove successful. Even when two locations share similar depths, the pathways leading to those depths matter. Research from the recent crewed expeditions continues to be examined, and many observations remain under analysis. Samples, imagery, and measurements gathered from the fracture zone are gradually adding detail to a region that has spent much of scientific history in obscurity. Each new dataset helps clarify how life responds to a landscape born from extension rather than collision. The Diamantina fracture zone therefore serves as a quiet reminder that depth alone does not define an ecosystem. Beneath the ocean, geology shapes possibility. The manner in which a place forms influences the chemistry, topography, and resources available within it. Two deep environments may appear similar on a map, yet the forces that created them can guide their destinies along entirely different paths, leaving distinct signatures in both stone and life. If the Indian Ocean could be reduced to a single moving point, a place where its past and future meet at once, it might be found far from any continent, hidden beneath open water east of Madagascar. There, beneath thousands of meters of sea, lies a geological crossroads whose influence extends across an entire ocean basin. No coastline marks its location, no island rises directly above it, yet this remote region quietly governs the shape of the Indian Ocean itself. Known as the Rodrigues Triple Junction, it occupies a position roughly 2,200 kilometers east of Madagascar. At this submerged intersection, three enormous tectonic plates meet: the African plate, the Indo-Australian plate, and the Antarctic plate. Their boundaries converge in a configuration so unusual that it remains unique within the Indian Ocean. From this point, three mid-ocean ridges extend outward across the seafloor like the branches of a vast geological network. The Central Indian Ridge stretches northward. The Southeast Indian Ridge angles toward the southeast. The Southwest Indian Ridge extends toward the southwest. Together, they form a ridge-ridge-ridge triple junction, a rare arrangement where three spreading centers connect at a single location. The feature was formally recognized in the early 1970s and later named after Rodrigues Island, situated roughly 1,000 kilometers to the northwest. Although the island itself occupies only a small area of land, its name became attached to one of the most significant tectonic structures on the planet. Unlike mountain ranges on land, these ridges are not static formations. They are active boundaries where new oceanic crust is continuously created. Deep beneath the seafloor, heat from Earth's interior drives the slow ascent of molten material. As tectonic plates move apart, magma rises into the gap, cools, and solidifies. Fresh crust forms, and the ocean basin expands by tiny increments almost too small to perceive in a single lifetime. Yet not all three ridges behave in the same way. The Central Indian Ridge and the Southeast Indian Ridge spread at intermediate rates, each moving outward by roughly a few centimeters per year on either side. Their activity produces characteristic ridge systems with recognizable volcanic features and relatively consistent topography. The Southwest Indian Ridge follows a different rhythm. It is among the slowest spreading ridges on Earth, advancing at less than a centimeter per year on each side. Such a modest pace profoundly influences its appearance. Near the triple junction, the ridge develops unusually deep valleys that descend between approximately 4,300 and 5,000 meters below sea level. These depressions differ from those found along faster spreading systems and lack some of the volcanic characteristics typically associated with more active ridges. The result is a landscape shaped as much by absence as by creation. Where magma supply is limited, tectonic stretching leaves deeper scars. The seafloor becomes rugged, broken, and complex, preserving evidence of the delicate balance between crustal formation and tectonic separation. For geologists, the Rodrigues Triple Junction functions almost like a living laboratory. The interaction of three plates allows scientists to observe how spreading centers influence one another across immense distances. Every ridge carries information about the forces acting beneath the ocean basin. Variations in spreading rate, volcanic activity, and crustal structure all contribute to a broader understanding of how oceans evolve through time. Its significance extends beyond geology alone. The ridges influence ocean circulation, seafloor habitats, and the distribution of marine ecosystems. Their elevated topography alters deep currents and creates environmental conditions distinct from the surrounding abyssal plains. Over geological timescales, these structures become foundations upon which biological communities establish themselves. Perhaps most remarkable is the continuity of the process. The forces operating at the Rodrigues Triple Junction today are part of the same story that began when Gondwana first started to fragment roughly 180 million years ago. The continents that once fit together have long since drifted apart, yet the mechanism responsible continues its patient work beneath the sea. Millimeter by millimeter, year by year, new crust emerges, and the Indian Ocean widens. The change is imperceptible in any single moment, but accumulated across millions of years, it reshapes entire oceans. At the Rodrigues Triple Junction, Earth's crust remains in motion, quietly extending a process that has never truly stopped since the ancient world first began to break apart. Beneath the spreading ridges of the Indian Ocean, seawater begins a journey that seems almost impossible. It slips downward through fractures in the oceanic crust, descending into layers of rock heated from below by molten material rising from Earth's interior. Far beneath the seafloor, the water changes. It absorbs heat, reacts chemically with surrounding minerals, and becomes part of a hidden circulation system operating beyond sight. Eventually, it returns upward, carrying the deep chemistry of the planet back into the ocean. In August of 2000, a Japanese scientific expedition brought one of these concealed worlds into view. Working from the research vessel Kare and deploying the remotely operated vehicle Kaiko, scientists explored an area near the Rodrigues Triple Junction. What they found transformed understanding of the Indian Ocean and expanded the known geography of life itself. The discovery was the first hydrothermal vent field ever identified in the Indian Ocean. The site became known as the Kare Vent Field. It lies approximately 2,460 meters beneath the surface on a small volcanic rise called Hakuho Knoll, situated north of the Triple Junction along the Central Indian Ridge. Though isolated within the vastness of the ocean basin, it revealed a landscape unlike the surrounding seafloor. Hydrothermal vents form where seawater penetrates deep into fractured crust and encounters intense subterranean heat. As the water circulates through hot rock, it becomes enriched with dissolved minerals and chemical compounds. When it eventually escapes back into the ocean, it emerges as a superheated fluid carrying the geochemical signature of the Earth's interior. At Carai, vent fluids exceed temperatures of more than 330 degrees Celsius. Under normal surface conditions, water this hot would rapidly boil into steam. Yet the immense pressure of the deep ocean prevents that transformation. The fluid remains liquid as it pours from openings in the crust and enters water only slightly above freezing. The meeting of these two environments produces one of the most remarkable spectacles on the planet. Dissolved minerals suddenly cool and precipitate from solution, accumulating layer by layer around the vent openings. Over time, towering chimney structures emerge from the sea floor. Some rise many meters into the darkness, their surfaces built from metal sulfides rich in iron, copper, and zinc. They grow gradually through the continuous interaction between heat, water, and stone, becoming geological monuments shaped by chemistry rather than erosion. Yet the true significance of Carai extended beyond geology. The vent field revealed a form of biological productivity that does not depend upon sunlight. Across most of Earth, ecosystems ultimately draw their energy from the sunday. Here, however, life follows a different path. Microorganisms inhabiting hydrothermal vents use chemical reactions as their source of energy. Bacteria and archaea harvest compounds such as hydrogen sulfide, methane, and hydrogen itself. Through chemosynthesis, they transform inorganic chemicals into organic matter, creating the foundation for entire ecosystems. In this environment, chemistry performs the role normally played by sunlight. The discovery demonstrated that the Indian Ocean contained its own deep biological provinces, sustained by these hidden energy sources. Not long afterward, another vent system, known as the Edmund Vent Field, was identified nearby at a depth of approximately 3,290 meters. Additional sites, including Solitaire and Dado, were later discovered along the central Indian Ridge, revealing that Carai was not an isolated anomaly, but part of a broader chain of chemosynthetic habitats scattered across the ocean floor. Among these locations, Carai remains especially intriguing because of its unusually hydrogen-rich fluids. The abundance of hydrogen supports communities of microorganisms adapted to extreme conditions. Some belong to a group known as hyperthermophiles, organisms capable of thriving at temperatures exceeding 80 degrees Celsius. Rather than living only around the vent openings, many occupy microscopic spaces within the rock itself, forming hidden ecosystems beneath the visible structures. Their existence expands the concept of where life can persist. Deep below the ocean, within heated stone and circulating fluids, entire communities flourish beyond the reach of sunlight. Around the vents, the seafloor becomes a rare oasis of abundance, a place where the Earth's internal heat rises into the ocean and sustains living systems through chemistry alone, linking the restless geology of the planet to some of its most extraordinary forms of life. Around the hydrothermal chimneys, the seafloor can become so densely occupied that the underlying rock nearly disappears from view. Layer upon layer of living bodies cluster against mineral towers, gathering wherever the chemistry of the vents is strongest. From a distance, these masses resemble dark, shifting blankets draped across the structures. Only when cameras move closer does the crowd resolve into thousands upon thousands of individual shrimp packed together in remarkable abundance. Among the most distinctive inhabitants of the Indian Ocean vent fields is a species known as Rimicaris cairae. It thrives in places where superheated fluids emerge from the crust, occupying a narrow boundary between conditions suitable for life and conditions that would quickly become fatal. The shrimp gather around the chimneys in enormous aggregations, forming some of the most conspicuous biological communities yet discovered in the deep Indian Ocean. Their success comes from an unusual partnership. Most animals must search for food somewhere beyond themselves. Rimicaris cairae carries its primary food source within its own body. Inside an enlarged chamber beneath the front portion of the shell lives a dense population of chemosynthetic bacteria. These microscopic organisms use chemicals dissolved within vent fluids, particularly compounds rich in sulfur and iron, as a source of energy. Through their metabolism, they transform inorganic substances into organic material, creating nourishment in a world completely disconnected from sunlight. The shrimp benefits directly from this arrangement. Rather than harvesting drifting food particles or hunting prey, it cultivates a living microbial community. In a very real sense, the animal farms bacteria upon itself. This relationship shapes nearly every aspect of its behavior. The shrimp positions its body carefully within the flow of vent water, balancing exposure to chemically rich fluids against the dangers of excessive heat. The bacteria require access to those compounds in order to thrive. By maintaining the proper position, the shrimp provides ideal conditions for its microscopic partners, which in turn provide nutrition. Life around a hydrothermal vent demands extraordinary precision. A small movement away from the vent can reduce the chemical resources necessary for survival. A small movement toward it can expose an organism to temperatures capable of causing severe damage. The shrimp, therefore, inhabits a remarkably narrow environmental corridor, guided by adaptations refined over immense spans of evolutionary time. One of the most intriguing of those adaptations involves vision. Conventional eyes offer limited value in the perpetual darkness of the deep ocean. Rimicaris cairae possesses greatly reduced eyes, yet it has not abandoned light detection entirely. Along its back lies a specialized photoreceptive structure, a broad sensory organ capable of detecting faint emissions associated with hydrothermal activity. Researchers believe this organ allows the shrimp to perceive the subtle thermal glow produced by superheated vent fluids. It does not create images in the way a typical eye would. Instead, it functions more like a detector, helping the animal maintain its position within the delicate boundary separating survival from danger. Even among populations of the same species, local conditions leave visible marks. Shrimp living at the cairae vent field commonly possess dark, almost black cephalothoraxes. At the nearby Edmund vent field, individuals more often display brown coloration in the same region. Scientists attribute these differences to variations in vent chemistry and the bacterial communities associated with each population. The colors therefore reflect not only the shrimp themselves, but also the environmental conditions surrounding them. Their story extends beyond the Indian Ocean. Rimicaris cairae bears a striking resemblance to a related species, Rimicaris exoculata, found thousands of kilometers away along the mid-Atlantic ridge. Despite the immense distance separating the two populations, their anatomy, lifestyle, and ecological roles remain remarkably similar. Such resemblance hints at an ancient connection embedded within the geological history of the oceans. Long before the present arrangement of continents and basins emerged, pathways may have existed that allowed ancestral populations to spread across connected ridge systems. Over time, those routes disappeared as tectonic plates shifted and oceans evolved, yet traces of that shared history remain visible in the bodies of these shrimp. Clustered around mineral towers in the darkness, Rimicaris caere represents a partnership between animal and microbe, geology and biology. Its survival depends not on sunlight, drifting food, or distant ecosystems, but on the chemical energy rising directly from the Earth's interior, transformed through living bacteria into a form that sustains an entire community at the edge of the planet's hidden furnace. Classification is one of science's quiet ways of revealing hidden patterns. A map can show where mountains stand or where oceans begin, but living organisms create maps of their own. Species spread, separate, adapt, and diversify, leaving behind clues about ancient connections. In the deep sea, those clues often appear in unexpected places, written not in rock but in the bodies of animals living around hydrothermal vents. Long before researchers explored the vent fields of the Indian Ocean, marine biologists had already divided the world's hydrothermal ecosystems into 5 major biogeographic provinces. Each province represented a distinct evolutionary neighborhood, a collection of species shaped by shared histories and environmental conditions. Though separated by great distances, the organisms within each province tended to resemble one another more closely than they resembled vent communities elsewhere. For a time, it seemed reasonable to assume that any vent ecosystems discovered in the Indian Ocean would belong to one of those existing groups. After all, oceans are connected, and deep water currents provide pathways through which larvae and microorganisms can travel. The expectation was that the Indian Ocean would simply extend a biological pattern already recognized elsewhere. The discoveries at the Caray and Edmund vent fields challenged that assumption. As scientists examined the invertebrates living around these hydrothermal systems, they found a combination of traits unlike those documented in any previously recognized province. The differences were not minor variations within a familiar community. They were substantial enough to justify the creation of an entirely new category. The Indian Ocean vent fields were designated as the world's 6th hydrothermal vent biogeographic province. This recognition carried important implications. It meant the Indian Ocean possessed its own evolutionary identity rather than serving merely as a continuation of neighboring regions. Its vent ecosystems represented a distinct chapter in the history of life, shaped by unique combinations of geography, geology, and time. Yet the deeper researchers looked, the more complex that identity became. Many organisms inhabiting the Indian Ocean vent fields showed close evolutionary relationships with species from the Western Pacific. Their anatomical similarities suggested ancient connections stretching back through millions of years. Some scientists propose that these relationships may reflect biological pathways established during the existence of the Tethys Sea, the ancient ocean whose remnants helped give rise to the Indian Ocean itself. At the same time, another signal emerged from the data. The dominant shrimp of the region, Rimicaris caere, closely resembled relatives inhabiting hydrothermal vents along the mid-Atlantic ridge. Its similarities pointed toward a different historical connection, one linking the Indian Ocean not to the Pacific, but to the Atlantic. The result was a community that seemed to draw ancestry from multiple directions at once. Researchers described this pattern using a technical phrase, noting asymmetric assembly rules biased toward Pacific evolutionary alliances. Beneath the scientific language lay a simple idea. Most components of the Indian Ocean vent fauna appear to trace their origins toward Pacific lineages, while a smaller but significant group reflects ties to Atlantic ancestors. This unusual mixture mirrors the geography of the Indian Ocean itself. Positioned between the Atlantic and Pacific basins, it occupies a central location within the global ocean system. Deep water connections link it to both neighboring oceans, creating opportunities for dispersal over immense timescales. The vent communities appear to preserve evidence of those ancient exchanges. Despite these connections, many species remain entirely unique. Studies suggest that 70% or more of the organisms inhabiting Indian Ocean vent systems are endemic. They exist nowhere else on Earth. Their evolutionary histories unfolded within this region alone, producing forms of life found only around these isolated sources of chemical energy. The degree of isolation is striking because the vent fields themselves are separated by vast stretches of seafloor. Carré, Edmund, Solitaire, and Dudu function like distant islands scattered across a dark ocean floor. For species to persist, larvae must somehow travel between them, crossing environments that may be unsuitable for adult life. How that movement occurs remains an active area of research. Ocean currents, larval behavior, and geological history likely all play roles in connecting these scattered habitats. For now, the pathways remain partly hidden, threading invisibly through deep water. The sixth province, therefore, stands as more than a classification. It is evidence that even in the most remote reaches of the Indian Ocean, evolution has followed its own course, blending ancient connections with remarkable independence to create a community unlike any other on the planet. Some discoveries arrive not as a single revelation, but as a procession. One specimen emerges from a net, then another still, each stranger than the last, until the growing collection begins to resemble a catalog from an unfamiliar world. During late 2022, such a procession unfolded in the eastern Indian Ocean as scientists explored a region that had remained largely unseen beneath the sea. The voyage began when Australia's National Science Agency, working alongside researchers from Museum's Victoria Research Institute, sent the research vessel Investigator toward the Cocos Islands Marine Park. The protected area had only recently been established, extending environmental safeguards across a vast section of ocean that had never been surveyed in detail at great depth. Beneath the surface stretched landscapes known largely through inference and scattered measurements. What existed there remained uncertain. For 35 days, the vessel crossed approximately 11,000 kilometers of ocean. Sophisticated mapping systems scanned the seafloor, while scientific equipment sampled habitats extending to depths of roughly 5 kilometers. Day after day, instruments descended into darkness and returned carrying fragments of an ecosystem few human beings had ever observed directly. The mapping alone transformed understanding of the region. Hidden beneath the water were broad, flat-topped seamounts, crowned with volcanic cones. Sharp ridges cut across the seafloor. Deep canyons carved pathways through submerged terrain. Ancient volcanic formations rose from the abyss, preserving geological histories written over immense spans of time. Entire landscapes appeared on scientific charts for the first time. Yet it was the biological collections that drew the greatest attention. Thousands of specimens emerged from the expedition's trawls. As researchers began sorting and examining them, a remarkable possibility became clear. According to expedition leader Tim O'Hara, roughly a third of the collected organisms might represent species entirely new to science. The estimate hinted at how little of the deep Indian Ocean has been explored. Even now, a single expedition can reveal animals unknown to scientific literature. Among the discoveries was a blind eel, unlike any previously documented. Its body was covered in loose, transparent, gelatinous skin through which underlying structures could faintly be seen. Unlike most fish, which reproduce through eggs, this species gives birth to live young. In the cold darkness of the deep ocean, it had evolved a reproductive strategy that differs from many of its relatives. Other creatures seemed equally improbable. Deep-sea batfish moved across the seafloor using modified fins that function almost like limbs. Rather than swimming continuously through the water column, they traversed the bottom with deliberate movements, conserving energy in an environment where resources can be scarce. High-fin lizardfish appeared with mouths lined by formidable teeth, adaptations suited to a life in which prey opportunities may be infrequent and impossible to waste. Pelican eels emerged from the collections as well, their enormous expandable jaws creating silhouettes unlike those of conventional fish. Slender snipe eels, elongated and delicate in form, added another variation to the extraordinary diversity of deep ocean anatomy. Viperfish carried their own unmistakable design, their long fangs projected from jaws engineered for ambush predation in darkness. Nearby, flatfish displayed one of the strangest transformations in vertebrate development. Both eyes occupied the same side of the head, the result of a remarkable migration process that occurs as the fish matures. For researchers, such as Yi Kai T of the Australian Museum, these animals represented more than curiosity. He described them as masters of their realm, a phrase that reflected the immense challenge of surviving at depths between 3 and 5 kilometers. Every species, collected during the voyage, embodied solutions to environmental conditions that remain difficult for humans even to visit. The expedition eventually returned to port, but the work it generated was only beginning. Samples required identification, genetic analysis, comparison with museum collections, and formal scientific description. The process moves carefully, often taking years before conclusions are published. As a result, much of what the voyage revealed remains in the process of being understood. Shelves, laboratories, and databases now hold pieces of a hidden ecosystem gathered from the abyss. Within those collections rest stories still being assembled, each specimen contributing another small glimpse into the vast and largely unexplored living gallery of the deep Indian Ocean. Not every deep-sea predator is built for speed. In the immense darkness of the abyss, where energy is scarce and opportunities arrive unpredictably, some animals have abandoned the pursuit of motion altogether. Rather than chasing prey through the water, they allow the landscape itself to become part of their strategy. They settle onto the seafloor, become almost indistinguishable from their surroundings, and wait. Among the creatures documented during the surveys near the Cocos Islands were deep-sea batfish, animals whose appearance seems to belong to a different set of evolutionary rules. At first glance, they scarcely resemble fish at all. Their bodies are flattened into broad discs, pressed close to the seabed. Their proportions appear unusual, almost architectural, as though they were designed specifically to occupy the narrow boundary between water and sediment. Movement reveals just how different they are. Most fish navigate by swimming. Batfish largely avoid that approach. Their pectoral and pelvic fins have evolved into sturdy appendages capable of supporting the body against the seafloor. Using these modified fins, they progress across the bottom in a slow and deliberate manner. Each movement resembles a cautious step more than a swimming stroke, carrying the animal gradually across the sediment while expending relatively little energy. This method of travel reflects the economics of the deep ocean. In shallower waters, active swimming may offer access to abundant food and opportunities. Far below the surface, conditions are different. Resources can be widely dispersed, and every burst of effort carries a metabolic cost. Over millions of years, the batfish lineage arrived at a solution based not on speed, but efficiency. Their bodies reveal the same priorities. The flattened shape keeps them close to the seabed, where prey is more likely to be encountered. Their skin possesses an armored quality that provides protection while maintaining a lifestyle closely tied to the bottom. The overall design favors stability and patience rather than rapid movement through open water. Patience, however, is only one part of the strategy. Projecting from the front of the head is a small structure known as the elysium. Though modest in appearance, it serves one of the most remarkable functions found among deep-sea fishes. The elysium is a modified dorsal fin spine transformed into a specialized lure. Extending from a hollow near the snout, it can be presented to nearby animals as an enticing object within the darkness. Small crustaceans and worms investigating the lure may unknowingly move within striking range. The batfish remains almost motionless, conserving energy until the precise moment an opportunity appears. Then the predator acts. The concept resembles the strategy employed by anglerfish, which also use modified structures to attract prey. Yet the setting is different. Anglerfish typically operate within the water column, suspended in the surrounding darkness. Batfish conduct their ambushes directly upon the seafloor, turning the sediment itself into part of the hunting ground. Such an approach is especially effective in environments where meals may be separated by long intervals. Days can pass without a feeding opportunity. In some circumstances, even longer periods may occur between successful captures. Under those conditions, restraint becomes as valuable as aggression. The ability to remain still, to wait without unnecessary expenditure of energy, can determine survival. What appears unusual to human observers is often the result of extraordinary specialization. Every feature of the batfish reflects adaptation to a particular ecological niche. Walking instead of swimming, luring instead of pursuing, waiting instead of searching, all represent solutions to challenges presented by life in the deep ocean. When images from the expedition reached the wider world, the batfish quickly became one of its most recognizable discoveries. Wide, set eyes, rounded features, and a puckered mouth gave the animal an appearance many people found unexpectedly charming. Yet beneath that curious exterior lies a highly refined predator, shaped by millions of years of evolution within one of the most demanding environments on Earth. On the deep sea floor, where every movement matters and every meal must be earned carefully, the batfish succeeds not through speed or strength, but through stillness, efficiency, and patience. A few thousand meters beneath the surface, color begins to lose its meaning. The familiar brightness of the upper ocean fades gradually through layers of blue until even that final trace disappears. At depths beyond roughly 1,000 meters, sunlight no longer reaches the water. There is no dawn, no sunset, no shifting weather overhead. Darkness becomes permanent, stretching across immense distances and geological ages. Yet the deep Indian Ocean is not truly dark. Life has found a way to manufacture its own illumination. Long after photosynthesis becomes impossible, countless organisms continue producing light through chemistry alone. Research from the Monterey Bay Aquarium Research Institute has suggested that roughly 3/4 of deep-sea animals are capable of bioluminescence, generating flashes, glows, pulses, and signals through reactions involving a molecule called luciferin and an enzyme known as luciferase. Together, they create one of the most widespread forms of communication in the largest habitat on Earth. Unlike the sunlight that powers surface ecosystems, this light is intimate. It exists in tiny bursts, often no brighter than a distant star. Entire conversations unfold in darkness through signals that may last only a fraction of a second before vanishing again into black water. Among the animals documented during the surveys around the Cocos Islands, few embody this hidden economy more dramatically than Sloane's viperfish. Its appearance seems almost unreal. A narrow predator armed with fangs so long that they remain visible even when the mouth is closed. Along its body are specialized light-producing organs called photophores. Additional luminous structures occur near the tip of an elongated dorsal fin ray that projects forward like a fishing line suspended in darkness. The strategy is elegantly simple. Small animals investigating the glow move closer, drawn toward what appears to be food or perhaps another living creature. The distance closes. The enormous jaws open. The encounter ends almost instantly. Elsewhere, in the deep Indian Ocean, another hunter has adopted a different approach. The stoplight loosejaw possesses one of the most unusual visual systems known among fishes. Most deep-sea organisms are sensitive primarily to blue wavelengths, the colors that travel farthest through seawater. Red light is effectively invisible to them. The loosejaw exploits this limitation. It produces red bioluminescence, creating a private beam of illumination that many surrounding animals cannot detect. Prey may drift through the darkness, completely unaware that it has been spotlighted. The predator observes what remains hidden from others, transforming an apparent disadvantage into a remarkable hunting tool. Bioluminescence serves many purposes beyond predation. Some species use it to locate mates across vast expanses of water where encounters may be rare. Others employ sudden flashes to confuse attackers, buying precious moments to escape. In the dimmer reaches above the abyss, certain animals generate light across their undersides in a technique called counter-illumination, matching the faint glow filtering from above and reducing their silhouette when viewed from below. Every use carries a cost. Producing light requires energy, and energy is among the most valuable resources in the deep ocean. As depth increases and food becomes scarcer, extravagant displays become less common. In the hadal regions explored earlier, where trenches sink into the greatest depths of the Indian Ocean, bioluminescence grows noticeably more restrained. The hadal snailfish offers a striking example. It does not generate its own light. Instead, it relies on vision adapted to detect the faintest glimmers produced by other organisms. In an environment where calories arrive slowly and unpredictably, observing another creature's signal may be more efficient than creating one. Across this immense underwater realm, every flash carries meaning. A pulse of blue, a brief green shimmer, a hidden red glow. Each represents a choice shaped by evolution and necessity. Light can reveal food, companionship, territory, or danger. It can advertise a presence or conceal one. In a world where darkness is the natural state, illumination has become one of the most valuable resources life can possess, spent carefully, exchanged sparingly, and woven into the daily survival of creatures living far beyond the reach of the sun. Across great stretches of the abyssal plain, the seafloor appears almost empty. Fine sediment settles slowly through the water column and spreads across the bottom in broad expanses that can continue for hundreds of kilometers with little interruption. There are no forests, no reefs, and no towering structures rising above the mud. Yet, scattered across this seemingly uniform landscape are delicate constructions that resemble tiny sandcastles, fragile monuments assembled grain by grain in one of the most remote environments on Earth. Their builders are among the strangest forms of life ever discovered. A xenophyophore is not a colony, nor a collection of cooperating organisms. It is a single cell. Despite that simplicity, some xenophyophores grow to nearly 10 centimeters in diameter, making them among the largest single-celled organisms known to science. On the abyssal plains of the Indian Ocean, where depths commonly range between 4,000 and 5,000 meters, these remarkable protists quietly shape the character of the seafloor around them. Seen from a distance, a xenophyophore can resemble a small mound, a lacework basket, or a tangled cluster of sediment held together by invisible threads. Its structure, known as a test, is built from particles gathered directly from the surrounding seabed. Tiny grains of mineral sediment are selected and assembled with organic secretions, creating a framework that can persist long after the living cell itself has vanished. Within this architecture lies the organism's true body, a branching network of living protoplasm called the granular system extends through the test in countless microscopic pathways. It winds through chambers and passages much as roots spread through soil, occupying a structure far larger than most single cells could ever achieve. The result is a creature that blurs the boundary between what appears simple and what appears complex. Part of that complexity comes from an unusual habit. Xenophyophores accumulate substantial quantities of waste material inside their tests. This material, known as stercomer, can occupy most of the organism's volume. In some species, more than 2/3 of the structure consists not of living tissue, but of stored waste. What might seem inefficient instead becomes part of a larger design, contributing to the elaborate interior landscape that develops within the test. On the abyssal plain, structure is often more important than size. A bare sediment surface offers few places for small animals to hide, feed, or reproduce. Any object rising above the mud can become valuable real estate. Xenophyophores provide exactly that. Their intricate frameworks create miniature habitats that interrupt the otherwise flat seafloor, producing pockets of shelter and complexity where life can gather. Researchers have repeatedly found that small invertebrates occur in much greater numbers around xenophyophores than in the surrounding sediment. Isopods crawl through their chambers. Nematodes occupy protected spaces between collected grains. Polychaete worms move among the crevices and tunnels. Each structure becomes a tiny island supporting a concentration of life far greater than the empty plain around it. The ecological importance of these giant cells became even more remarkable through a discovery made far from the Indian Ocean, off the coast of Costa Rica. There, scientists observed snailfish from the genus Paraliparis using xenophyophores in an unexpected way. The fish deposited eggs deep within the cellular structures, inserting them through specialized ovipositors and leaving the developing embryos protected inside the labyrinth of passages and chambers. For the first time, a vertebrate had been documented using a single-celled organism as a nursery. The discovery transformed the way scientists viewed these unusual protists. They were no longer simply curious inhabitants of the deep seafloor. They were ecosystem engineers, creating shelter, concentrating biodiversity, and supporting relationships that extended across entirely different branches of life. Throughout the world's abyssal regions, xenophyophores continue this quiet work. Across the Indian Ocean's immense muddy plains, these giant cells stand as delicate architects of complexity, proving that even a single cell can reshape an entire landscape and provide a home for countless others in the vast stillness of the deep. Far above the abyssal plains, sunlight pours across the surface of the Indian Ocean each day, illuminating drifting plankton, warming shallow waters, and powering one of the largest biological systems on the planet. Yet almost none of that abundance remains where the ocean is deepest. By the time life reaches the sea floor thousands of meters below, it arrives only as a slow and scattered descent, a constant fall of fragments crossing an immense vertical wilderness. Oceanographers call this drifting material marine snow. The name captures its movement more than its appearance. Seen through submersible lights, individual particles drift downward from the darkness above with an unhurried grace, moving through still water like flakes settling through a winter night. Each particle carries traces of a distant world, tiny remains of phytoplankton, discarded shells, dead larvae, shed mucus, fragments of larger organisms, and dense pellets produced by zooplankton gradually gather into clumps held together by sticky biological compounds. These fragile aggregates begin their journey near the surface, where sunlight supports photosynthesis and energy is abundant. From there, they descend through layer after layer of ocean, entering regions where the conditions become progressively colder, darker, and more demanding. The voyage is remarkably long. A single particle may require weeks or even months to complete its passage from the illuminated surface to the abyssal floor. Few particles arrive intact. Throughout the water column, countless organisms intercept this falling material. Small crustaceans graze upon it, bacteria decompose it, filter feeders remove portions from the drifting stream. Each encounter extracts energy, reducing the amount that continues downward. By the time the journey ends, only a tiny fraction remains. Scientific estimates suggest that merely 1 to 3% of the organic carbon produced near the surface ultimately reaches the abyssal seafloor. The plains below survive on this residue. Between the trenches, hydrothermal systems, and fractured mountain chains explored earlier, most of the Indian Ocean floor consists of broad abyssal plains extending across depths of roughly 4,000 to 5,500 meters. These immense sedimentary landscapes cover more area than all other deep-sea habitats combined. They form the largest continuous ecosystems on Earth, yet their entire biological foundation depends upon the steady arrival of food produced far above. Every organism living there has evolved within the limits imposed by scarcity. Energy is precious. Nothing can be wasted. Growth proceeds slowly. Metabolism remains conservative, and survival often depends upon extracting the smallest possible benefit from each particle that settles onto the sediment. Among the most visible inhabitants are the holothurians, commonly known as sea cucumbers. Moving patiently across the seafloor, they process vast quantities of sediment in search of organic matter. Some species advance like living vacuum cleaners, drawing surface mud into their bodies and separating nutritious particles from mineral grains. Others extend feeding structures into the water above, capturing suspended material before it reaches the bottom. Around them live brittle stars, their flexible arms spread across the sediment like delicate branches. Polychaete worms tunnel through buried layers, recycling nutrients hidden beneath the surface. Burrowing bivalves occupy deeper sediments, filtering and processing material that has accumulated over long periods. Each species fills a different ecological role, participating in a system sustained by resources so limited that almost every available niche has value. The pace of life reflects these conditions. Where shallow ecosystems may transform within seasons, abyssal communities often change across years or decades. Individual organisms can require long periods to mature. Reproductive cycles may unfold slowly, synchronized with rare opportunities rather than predictable abundance. Biological accumulation becomes a gradual process measured not in days, but in generations. Because renewal is so slow, disturbance carries unusual consequences. A single disruptive event can erase patterns that require decades to develop. Sediment displaced by human activity, whether from trawling, mining equipment, or drifting plumes, may bury organisms, alter habitats, and interrupt ecological relationships that depend upon stability. And so the abyssal plain endures through patience. Far beneath the bright surface world, life persists on a continuous rain of distant nourishment, each drifting particle completing a journey measured in months, sustaining communities that have learned to flourish on the smallest of gifts descending from above. Far beneath the living surface of the Indian Ocean, beyond the reach of waves, storms, and seasons, an immense reserve is quietly at work. It has no visible machinery and produces no sound. Yet, over millions of years, it has helped regulate the composition of the atmosphere and shape the climate experienced by every living creature on Earth. Hidden within dark basins and buried sediments lies one of the planet's most powerful long-term stabilizing systems. Oceanographers call it the biological pump. Its operation begins where sunlight still penetrates the sea. Near the surface, microscopic phytoplankton absorb carbon dioxide from the atmosphere during photosynthesis, incorporating carbon into their bodies as they grow. That carbon then moves through the food web, passing into zooplankton, fish larvae, and countless other organisms. Eventually, portions of it begin a descent into deeper water, carried downward within the continuous stream of organic material that drifts from the surface world. Some of this carbon is recycled before it reaches great depth. Much of it is consumed, decomposed, or transformed along the way. Yet a fraction survives the journey. When organic matter sinks into the deep ocean and becomes incorporated into seafloor sediments, the carbon it contains is effectively removed from direct exchange with the atmosphere. Instead of remaining part of the rapidly cycling surface system, it enters storage measured not in years, but in geological time. In some cases, that storage may persist for thousands, hundreds of thousands, or even millions of years. The Indian Ocean plays a particularly important role in this process. Its surface waters include regions of remarkable biological productivity. The Arabian Sea, influenced by seasonal monsoon-driven circulation, supports vast blooms of plankton. Farther east, the waters surrounding Indonesia connect multiple oceanic systems and sustain rich biological activity. These productive regions continually generate organic material that begins the long descent toward the deep. Beneath them lie enormous basins capable of storing the products of that descent. Together, these deep waters form part of the largest active carbon reservoir on the planet. More carbon resides within the ocean than within the atmosphere, terrestrial vegetation, and soils combined. The deep Indian Ocean contributes substantially to that storage, acting as a vast archive where carbon can remain isolated from the atmosphere for extraordinary periods. Without this mechanism, Earth's climate would look very different. Atmospheric carbon dioxide concentrations would be significantly higher, altering global temperatures and influencing ecosystems across the planet. The biological pump operates slowly and invisibly, yet its cumulative influence extends across entire eras of Earth history. Its effects are recorded in the seafloor itself. Each layer of abyssal sediment preserves fragments of the conditions under which it formed. Tiny shells of foraminifera settle into the mud after death, carrying chemical signatures of ancient oceans. Clay particles, transported from distant continents, become incorporated into accumulating deposits. Ratios between organic and inorganic carbon shift in response to changing environmental conditions. Over centuries and millennia, these materials build a layered archive beneath the seabed. To scientists, these sediments function much like pages in a vast geological manuscript. Research vessels lower coring equipment through thousands of meters of water and extract long columns of mud from the abyssal plain. Within those cores, subtle variations reveal information about past temperatures, ocean productivity, circulation patterns, and atmospheric chemistry. Events separated by immense spans of time remain preserved within successive layers, compressed into a vertical record that can be read with remarkable precision. The stillness of the abyss helps maintain this archive. Sediments accumulate slowly, often only millimeters across long stretches of time, preserving delicate evidence of ancient climates. Yet, that same slowness also creates vulnerability. Disturbances to the seafloor can disrupt deposits that required centuries to form. Activities such as trawling, mining, or pollution may resuspend sediments, alter biological communities, and interfere with processes that contribute to long-term carbon storage. And so, the deep Indian Ocean serves not only as habitat, but as memory. Beneath its quiet plains rests a vast climate battery, charged grain by grain through the steady descent of organic carbon, preserving both the history of Earth's changing atmosphere and part of the mechanism that keeps it in balance today. If a traveler could drift across the floor of the central Indian Ocean basin, moving slowly above the sediment in the glow of a submersible's lamps, the landscape might at first appear unremarkable. The plain would stretch outward into darkness, broad and level, interrupted only by occasional traces left by burrowing animals. Then, scattered across the seafloor, small dark objects would begin to emerge from the mud. Some would resemble stones. Others would look like weathered potatoes resting where they had fallen long ago. Yet these quiet objects are among the most sought-after geological formations on Earth. They are polymetallic nodules, and they lie across vast regions of the abyssal plain at depths commonly ranging between 5,000 and 5,500 meters. Billions of them rest upon the sediment surface, each carrying a concentration of metals that modern technological societies consider increasingly valuable. Their appearance gives little hint of their significance. Most nodules consist primarily of manganese and iron hydroxides layered around a central core. Embedded within those layers are other elements, including nickel, copper, cobalt, and various rare earth elements. These materials are essential components in technologies that have become woven into daily life, from rechargeable batteries and electronic devices to electric vehicles and renewable energy systems. What makes the nodules especially remarkable is not merely their composition, but the pace at which they form. Unlike geological processes associated with volcanoes or mountain building, nodule growth proceeds with extraordinary patience. Dissolved metals present in seawater gradually precipitate onto a nucleus resting on the seafloor. That nucleus might be a fragment of rock, a piece of bone, or even the tooth of a long-vanished shark. Layer by layer, mineral coatings accumulate around it. The growth is almost unimaginably slow. A few millimeters may require an entire million years. A single nodule, large enough to fit comfortably in a human hand, may represent between 3 and 10 million years of uninterrupted accumulation. While continents shift, climates change, and species appear and disappear, the nodule continues its gradual expansion, recording the passage of deep time within its mineral layers. Across the central Indian Ocean basin, this process has produced immense deposits. Recognizing their potential value, nations began investigating these resources decades ago. India emerged as one of the earliest participants in this effort. During the late 1980s, it secured exploration rights through the International Seabed Authority, becoming a pioneer investor in the region. An area of 150,000 square kilometers was initially allocated for exploration activities. Following the relinquishment of half that territory, approximately 75,000 square kilometers remained under Indian control, an expanse larger than many sovereign nations. Within this area, estimates suggest the presence of hundreds of millions of tons of nodules containing substantial quantities of nickel, copper, and cobalt. Such figures have attracted scientific, industrial, and political attention, transforming portions of the abyssal plain into regions of strategic interest. Interest alone, however, does not make extraction possible. The technical challenges are immense. Machines designed to operate in darkness beneath thousands of meters of water must withstand crushing pressure while navigating soft sediment and maintaining reliable communication with the surface. Under India's deep ocean mission, engineers have developed and tested prototype mining systems. Early trials occurred in shallower waters near the coast before progressing to operations at depths exceeding 5,000 meters within the basin itself. Even so, commercial mining remains unrealized. The technology continues to evolve, and many practical obstacles remain unresolved. At the same time, scientific understanding of abyssal ecosystems is still developing. The same seafloor that contains valuable mineral resources also supports communities of organisms adapted to conditions that exist nowhere else on Earth. As a result, the nodules have become more than geological curiosities or industrial targets. They now stand at the center of one of the most consequential environmental discussions of the modern era. Across the deep Indian Ocean, these ancient mineral formations rest where they have grown for millions of years, holding both extraordinary material value and profound ecological significance within the same silent landscape. Long before any machine arrives, the abyssal plain appears almost motionless. Fine sediment stretches outward beneath the weight of thousands of meters of water, interrupted only by scattered nodules resting upon the seafloor like dark islands in a pale landscape. Around them, life persists at a pace so gradual that entire human civilizations could rise and vanish, while many of its inhabitants complete only a fraction of their existence. It is within this slow world that the debate over deep-sea mining becomes most profound. The metallic nodules scattered across the central Indian Ocean basin are often described as mineral resources, yet, to the organisms living among them, they are something else entirely. They are foundations. They are attachment points. They are the rare pieces of hard ground in a realm dominated by soft sediment. Many abyssal creatures cannot anchor themselves directly within loose mud. Sponges, xenophyophores, and numerous other sessile organisms depend upon solid surfaces to establish themselves. A single nodule may support an entire miniature community, providing stability in an environment where suitable substrate is exceptionally scarce. The relationship has developed over immense spans of time. As nodules slowly accumulated, layer by layer, through millions of years, biological communities adapted to their presence. Organisms settled upon them, reproduced around them, and incorporated them into the structure of abyssal ecosystems. What appears at first glance to be an inert stone is often a living platform supporting layers of biological activity invisible to a casual observer. A mining operation would begin by removing these foundations. Collector vehicles would travel across the seafloor, gathering nodules and the upper layer of sediment surrounding them. The process is frequently compared to harvesting, yet the comparison can be misleading. A harvested crop grows back, the nodules do not. Because their formation occurs at rates measured in mere millimeters across 1,000,000 years, the physical habitat being removed cannot be replaced within any timescale meaningful to human societies. Once collected, the substrate supporting countless organisms effectively disappears from the ecosystem. The consequences extend beyond the loss of the nodules themselves. As machines move across the abyssal plain, fine sediment would be disturbed and lifted into the surrounding water. Clouds of suspended particles, known as sediment plumes, could spread far beyond the immediate mining site. Ocean currents would carry these particles outward, allowing them to settle across large areas of seafloor. For animals that filter water to obtain food, such conditions may prove particularly challenging. Delicate feeding structures can become coated with sediment. Respiratory surfaces may be obstructed. Organisms adapted to clear abyssal conditions could find themselves buried beneath layers of newly deposited material. Even subtle disturbances matter in environments where change is normally rare. Many deep-sea species grow slowly, mature late, and produce relatively few offspring. Energy is limited, food arrives only in small quantities, and biological processes proceed at a measured pace. Recovery from disruption is therefore unlike recovery in coastal habitats or shallow ecosystems. Damage occurring within hours may require centuries to repair, and in some cases, the original community may never fully return. Researchers have sometimes reached for familiar comparisons to illustrate the scale of the issue. One of the most common likens deep-sea mining to clear-cutting an ancient forest. Yet even that analogy may underestimate the challenge. Forests can regenerate within hundreds of years. Portions of the abyssal plain operate on timelines vastly longer. Another difficulty lies in what remains unknown. Although exploration has expanded rapidly, much of the deep Indian Ocean remains poorly documented. New species continue to be discovered whenever scientific expeditions visit previously unsurveyed regions. Entire ecological relationships are still being uncovered. Some organisms have not yet received formal scientific names. Others are known only from a handful of observations. International regulations require environmental assessments before commercial extraction can proceed. Such requirements acknowledge the importance of understanding potential consequences. Yet many scientists note a fundamental limitation. Measuring loss requires knowing what exists in the first place. Across the silent plain, countless organisms continue their slow lives among structures that have taken millions of years to form. The question surrounding mining is therefore not only what resources lie on the sea floor, but how much of this ancient and still largely unseen world can be removed before its story is fully understood. A grain of sediment settling onto the abyssal floor seems insignificant. It drifts downward through darkness, joins countless other particles, and disappears into the quiet accumulation of the deep seabed. Yet, within some of those grains now lies a material that did not originate in any natural cycle of ocean chemistry or geology. It began instead in factories, cities, fishing fleets, and coastlines far above the sea. By the middle of the present decade, evidence of that journey had reached a troubling milestone. Scientists surveying polymetallic nodule fields within the central Indian Ocean basin recovered sediment from depths of roughly 5,000 meters and discovered microplastic fibers embedded within the seabed itself. The finding confirmed a suspicion that had been steadily growing through years of research across multiple oceans. Human plastic waste was no longer confined to beaches, surface waters, or coastal ecosystems. It had become part of the geological fabric of the deep Indian Ocean. The particles involved were extraordinarily small. Microplastics are fragments measuring less than 5 millimeters across. Some originate as larger objects that gradually fragment under sunlight, wave action, and physical abrasion. Others enter the environment already microscopic, released through industrial processes, synthetic textiles, fishing equipment, and countless everyday products. Once introduced into the ocean, these particles begin a journey shaped by currents, biology, and gravity. For many years, plastic was assumed to remain largely near the surface. Research gradually revealed a more complex story. Microscopic organisms colonize floating plastic fragments almost immediately. Bacteria, algae, and other microorganisms establish themselves upon the artificial surfaces, creating living coatings known as biofilms. As these biological communities grow, the density of the plastic increases. Eventually, many particles lose their buoyancy and begin descending into deeper water. The process resembles a slow transformation. An object originally designed to float becomes incorporated into the ocean's biological systems. Layer by layer, life weighs it down until gravity carries it toward depths where sunlight has never reached and where natural degradation proceeds at an exceedingly slow pace. Along the way, the particles become part of the same downward movement that transports organic matter into the abyss. They drift through midwater ecosystems, pass hunting fish and gelatinous animals, and continue toward the seafloor where they settle among sediments that accumulate grain by grain over centuries. Some of the deepest places on Earth appear particularly vulnerable to this process. Studies conducted in other oceans have shown that hadal trenches can function as enormous collection basins. Their funnel-shaped topography encourages the concentration of sinking material, while bottom currents often direct particles toward the deepest regions. Rather than remaining evenly distributed across the seafloor, microplastics may accumulate in extraordinary concentrations within these geological depressions. Research from the Pacific has documented remarkably high levels of microplastic contamination in sediments recovered from the Mariana Trench. In some samples, concentrations ranged from hundreds to thousands of particles within a single liter of sediment. Such findings transformed scientific understanding of pollution in the deep ocean. The deepest trenches were once imagined as remote refuges, isolated by distance, darkness, and immense pressure. Instead, they appear capable of collecting the remnants of human activity from across entire ocean basins. Within the Indian Ocean, scientists are still determining the full scale of the phenomenon. Precise concentrations within the hadal depths of the Java Trench remain the subject of ongoing investigation. Yet, the discovery of microplastic fibers at 5,000 meters carries its own significance. That depth lies far above the deepest trench floor, yet far below any environment most people will ever see. It occupies a realm once considered inaccessible and detached from events at the surface. The presence of synthetic particles there demonstrates that the pathways connecting the ocean are more complete than they first appear. Currents move water across vast distances. Organisms transport matter through food webs. Particles sink relentlessly through the water column. Over time, the deep Indian Ocean receives traces of nearly everything released into the sea. Even here, among ancient sediments accumulating in darkness, the signature of the modern world has arrived and quietly settled into the mud. When food finally arrives at the floor of the deepest trench, it rarely remains untouched for long. A dead fish, a drifting jelly, or a fragment of organic debris descending from distant surface waters quickly becomes the center of activity. From the darkness emerge small scavengers, moving across the sediment with quiet efficiency. Within hours, sometimes even minutes, the material begins to disappear beneath a living tide of amphipods. These crustaceans are among the most successful inhabitants of the hadal world. Though many measure only a few centimeters in length, deep-sea amphipods occupy a vital position within trench ecosystems. They are recyclers of the abyss, transforming fallen organic matter into living tissue and passing that energy onward through the food web. Wherever nutrients reach the trench floor, amphipods are often among the first animals to arrive. For many years, they were viewed primarily as evidence of biological resilience. Their ability to survive immense pressure, scarce food supplies, and permanent darkness made them ideal symbols of adaptation. Yet, as scientists began examining them more closely, these same creatures revealed something else. Hidden within their bodies was evidence that human influence had reached even the most remote parts of the ocean. A landmark study published during the closing years of the second decade of the present century examined amphipods collected from 6 of the deepest ocean trenches on Earth. These animals had been recovered from environments separated by vast distances, isolated from one another by entire ocean basins and immense geological barriers. Despite that isolation, the results showed a striking pattern. Researchers discovered microplastic particles and synthetic fibers within the digestive systems of the amphipods. The contamination was not confined to a single trench or a particular region. It appeared repeatedly across multiple locations, establishing the deepest confirmed record of microplastic ingestion known at the time. The finding altered the way scientists viewed pollution in the deep sea. Plastic was no longer simply accumulating within sediments or drifting through the water column. It was entering living organisms. Tiny fragments that originated far above the ocean surface had become incorporated into the diets of creatures inhabiting some of the least accessible environments on the planet. The implications extend beyond the amphipods themselves. In the hadal zone, energy moves through a relatively short and specialized food web. Amphipods consume organic material that settles from above, along with whatever particles accompany it. Predators then consume the amphipods. In the Java Trench, where snailfish patrol the seafloor as dominant vertebrate hunters, amphipods form a major component of the available prey base. Material entering the bodies of amphipods therefore gains a pathway into higher levels of the ecosystem. The concern is not limited to plastic alone. Investigations of hadal amphipods have also detected persistent organic pollutants, including compounds known as polychlorinated biphenyls. These industrial chemicals were banned decades ago in many parts of the world because of their environmental persistence and potential biological effects. Yet their presence within trench organisms demonstrates how long such substances can remain active within Earth's interconnected systems. Ocean currents transport them. Atmospheric circulation distributes them. Biological processes move them through food webs. Eventually, some portion reaches even the deepest basins. The remarkable irony is difficult to ignore. The hadal trenches were once imagined as distant refuges, protected by depth and isolation. Their immense pressures seem to place them beyond the reach of ordinary environmental disturbance. Yet the smallest scavengers reveal a different reality. They carry within their digestive tracts traces of materials created by societies thousands of kilometers away and often decades in the past. For scientists, amphipods have become more than scavengers. They are biological record keepers. Each individual feeds upon the particles descending through the water column and preserves evidence of what accompanies them. Through these small crustaceans, the deep ocean quietly records the movement of pollutants across the planet. Within the darkness of the Java Trench, where life persists beneath pressures almost beyond imagination, the smallest creatures now carry a message written not in words, but in fibers, fragments, and chemicals. Their bodies reveal that the boundary between the human world and the deepest ocean is far thinner than it once seemed. Sometimes the most detailed discoveries begin with an absence. Across the vast expanse of the southern Indian Ocean, ships crossed waters that seemed empty, searching for a single missing aircraft. The goal was narrow and urgent, focused on one event that had unfolded high above the sea. Yet as the search expanded outward into one of the least explored regions on Earth, attention gradually shifted toward a different mystery, one that lay far below the waves. When Malaysia Airlines flight MH370 disappeared during its journey from Kuala Lumpur to Beijing, an international effort emerged to determine where it had gone. Investigators reconstructed flight paths, analyzed satellite communications, and identified a remote region of the southern Indian Ocean as the most likely search area. It was a place far removed from major shipping routes, separated from the nearest Australian ports by immense distances, and underlain by seafloor that remained largely unknown. What followed became one of the largest deep ocean mapping campaigns ever undertaken. Between the middle years of the decade, specialized survey vessels methodically scanned more than 120,000 square kilometers of seabed. Using multi-beam echo sounders and side-scan sonar, they created detailed maps of terrain hidden beneath thousands of meters of water. The search area included depths approaching 6,000 meters and regions that had never before been surveyed with comparable precision. The work unfolded slowly. Survey ships moved back and forth across the ocean in carefully planned patterns, gathering data line by line. Each pass added another piece to a growing portrait of the seafloor. What emerged was not the smooth, featureless landscape many had imagined. Instead, the hidden floor of the Indian Ocean revealed extraordinary complexity. At the time, only a relatively small fraction of Earth's ocean floor had been mapped at such resolution. This search transformed one remote sector of the Indian Ocean into one of the most thoroughly surveyed deep ocean regions anywhere on the planet. The aircraft itself remained elusive. Yet the search uncovered a geological world few people suspected existed beneath those waters. Sonar images revealed underwater mountains rising from the abyssal plain. Some reached heights comparable to major peaks on land, deep valleys carved through the seafloor, while steep escarpments and elongated ridges stretched across the darkness in intricate patterns. Among the most surprising discoveries were extensive fields of mud volcanoes. Unlike volcanic mountains built from molten rock, these formations arise when sediment, fluids, and gases migrate upward from beneath the seabed. Over long periods, they construct broad structures that can tower hundreds or even thousands of meters above the surrounding terrain. Hidden beneath layers of water, they remain invisible from the surface and often escape detection until detailed mapping surveys pass overhead. One such formation demonstrated just how little was known about the region. A sonar towfish, suspended behind a survey vessel and designed to operate safely above the seafloor, collided with a massive mud volcano that had never been documented. The structure rose so dramatically from the surrounding landscape that it intercepted the instrument's path, sending the equipment to the bottom. Even in the midst of a highly sophisticated search, the ocean still possessed the ability to surprise those exploring it. The maps continued to accumulate. Scientists identified previously unknown ridges extending for dozens of kilometers. They documented canyons whose dimensions rivaled some of the most celebrated geological features on land. Isolated peaks emerged from the data like hidden islands buried beneath the sea. Each discovery expanded understanding of how the Indian Ocean basin had formed and evolved through geological time. Years later, interest in the region persisted. A renewed search effort employed fleets of autonomous underwater vehicles capable of operating independently across the deep seafloor. These robotic explorers carried increasingly advanced sensors, continuing the process of transforming blank spaces on ocean charts into detailed landscapes. The missing aircraft remained the reason the search began, yet the legacy of the effort extends beyond aviation. In seeking a single object lost within the immensity of the ocean, humanity produced one of the most detailed portraits ever assembled of a remote section of the deep Indian Ocean, revealing a hidden terrain that had waited unseen beneath the water for millions of years. Far below the reach of storms, currents, and memory, objects can disappear so completely that they seem to pass out of history itself. The abyssal floor of the Indian Ocean is scattered with traces of events that unfolded long before satellites, radio transmissions, or global communication networks connected the world. For most of human history, a ship that vanished beyond the horizon often left behind little more than silence. Families waited, ports speculated, records ended abruptly, and the sea kept its answer. In the immense southern reaches of the Indian Ocean, where distance alone can isolate a vessel from help, such disappearances were once an accepted part of maritime life. During the extensive surveys conducted in the search for Malaysia Airlines Flight MH370, researchers expected to encounter unfamiliar geological features. They anticipated ridges, canyons, mud volcanoes, and mountains hidden beneath the water. What they did not expect was to encounter evidence of entirely different journeys, preserved in darkness, thousands of meters below the surface. Among the discoveries were 4 previously uncharted shipwrecks resting on the ocean floor. The wrecks lay at depths approaching 4,000 meters, far beyond the reach of ordinary diving and far from regions where historical investigators had focused their attention. For generations they had remained undetected, concealed beneath an ocean whose floor had never been mapped in detail. Sonar images revealed scattered debris fields, anchors, fragments of cargo, and structural remains spread across the sediment. The vessels are believed to date from the 19th century, an era when sailing ships crossed the Indian Ocean carrying people, mail, timber, textiles, machinery, and countless other goods between Europe, India, Southeast Asia, and Australia. These routes formed some of the most important commercial pathways on Earth. Yet they also passed through waters capable of producing extraordinary violence. South of the major continental landmasses, uninterrupted winds circle the planet with remarkable force. Mariners gave these latitudes memorable names: the Roaring Forties and the Furious Fifties. The names were not poetic exaggerations. With little land to interrupt them, powerful westerly winds generated immense swells that could batter wooden vessels for days. Storm systems cross the ocean with tremendous energy, and ships caught within them faced dangers that could quickly become overwhelming. Somewhere within those waters, long before modern navigation transformed ocean travel, these vessels appear to have met their end. No distress calls reached distant ports. No aircraft searched overhead. No satellites tracked their final positions. The ships vanished into the same vast ocean that had carried them across the world, leaving only uncertainty behind. Once they settled on the seabed, darkness closed over them completely. Time continued its slow work. Wooden components became food for specialized marine organisms capable of consuming submerged timber. Metal structures gradually corroded under cold, pressurized conditions. Sediment accumulated across decks and cargo holds. Deep-sea animals colonized exposed surfaces, transforming artifacts of human industry into parts of the surrounding ecosystem. Decade after decade, the wrecks became less like ships and more like features of the seafloor itself. What makes their discovery especially striking is the manner in which it occurred. No expedition had set out to find these vessels. No historical records pointed directly toward their resting places. They were revealed only because sophisticated mapping technology happened to sweep across the area while searching for something entirely different. The episode offers a quiet perspective on the scale of the ocean. Even within an ocean crossed by shipping routes for centuries, entire shipwrecks can remain hidden for more than 100 years. Their existence can pass unnoticed through generations, preserved beneath kilometers of water without a single human observer. As survey technology gradually expands humanity's view of the seabed, each newly mapped region seems to reveal not emptiness, but layers of forgotten history, resting patiently on the floor of the Indian Ocean, where the passage of time moves with extraordinary slowness. A map can create the illusion of familiarity. A glance across a globe suggests certainty. Coastlines appear fixed. Ocean basins seem neatly defined. The blue spaces between continents look catalogued and understood, as though every valley, ridge, and plain has already been measured and named. Yet, far beneath the surface, beyond shipping lanes and satellite photographs, much of the Indian Ocean remains one of the least observed landscapes on Earth. Even in an age of spacecraft, global communications, and precision navigation, only a small fraction of the world's seafloor has been mapped using modern multi-beam echo sounder technology. Current estimates suggest that detailed mapping exists for only about 10 to 15% of the global ocean floor. The remainder is known through fragments, isolated surveys, and broad approximations stitched together across immense distances. The contrast becomes striking when placed beside other worlds. Humanity possesses more detailed topographic maps of the surfaces of the Moon, Mars, and Venus than it does of vast regions hidden beneath the Indian Ocean. Mountains on distant planets can often be described with greater precision than valleys lying beneath Earth's own waters. For much of the Indian Ocean, especially across its southern basin, scientists long relied on satellite gravity measurements rather than direct observation. Satellites can detect subtle variations in the ocean's surface caused by gravitational differences beneath the water. From these variations, researchers can infer the presence of underwater mountains, depressions, and ridges. The technique is powerful, but it remains indirect. It reveals broad outlines rather than fine detail, offering a sketch where a portrait is needed. Only when survey vessels pass overhead with multi-beam sonar does the seafloor emerge in high resolution. Suddenly, features once represented as vague humps become towering escarpments. Gentle depressions, transform into deep canyons. Entire geological structures appear where none had previously been recognized. The discoveries made during the search for Malaysia Airlines flight MH370 demonstrated this reality with unusual clarity. Areas thought to be relatively featureless revealed intricate landscapes of mountains, ridges, mud volcanoes, and steep valleys. The ocean floor proved not simpler than expected, but far more complex. The biological picture is equally incomplete. When scientists describe the creatures of the deep Indian Ocean, they are often drawing conclusions from an astonishingly small collection of observations. The deepest reaches of the Java Trench have received a single crude visit. The Dordrecht Deep within the Diamantina fracture zone has likewise been visited only once by humans. Hydrothermal vent systems along the central Indian Ridge have been examined by a limited number of expeditions scattered across decades. From these brief encounters have emerged unusual snailfish, previously unseen tunicates, shrimp sustained by chemosynthetic bacteria, vast microbial communities, and countless specimens that still await formal description. Nearly every expedition returns carrying records that expand known ranges, challenge assumptions, or introduce organisms entirely new to science. This pattern has become one of the defining characteristics of deep Indian Ocean exploration. Researchers descend with carefully planned objectives and often return with discoveries they never intended to seek. The consequence is a humbling one. Decisions concerning conservation, resource extraction, pollution, and long-term stewardship are being made while fundamental knowledge remains incomplete. Entire ecosystems may exist beyond the edges of current maps. Evolutionary lineages may persist in habitats that have never been sampled. Geological processes may be unfolding across landscapes that no human instrument has yet recorded in detail. The deep Indian Ocean is often described as remote, but remoteness alone does not capture its character. It is not a thoroughly explored realm containing a few remaining blanks. It is a largely unseen realm illuminated only by scattered points of observation, each expedition adding another small light to an immense darkness, gradually revealing a world whose true scale is only beginning to come into view. For most of Earth's history, the deepest parts of the Indian Ocean existed beyond the reach of human influence. Continents drifted across the planet. Ancient seas opened and vanished. Mountain ranges rose, eroded, and disappeared. Entire branches of life emerged and faded away. Through all of it, the abyss remained a place of remarkable continuity. In the darkness beneath thousands of meters of water, conditions changed with extraordinary slowness. Temperatures remained nearly constant. Salinity shifted little. Pressure endured with unwavering force. Generation after generation of deep-sea organisms inherited an environment that was, by geological standards, astonishingly stable. Within that stability, evolution worked patiently. The animals inhabiting the deepest regions of the Indian Ocean are not generalists capable of thriving anywhere. They are specialists, refined across immense spans of time. Every aspect of their biology reflects the demands of a particular world. Proteins function under crushing pressure. Cell membranes remain flexible where most life would fail. Reproductive strategies are calibrated to scarce food and infrequent encounters. Energy is conserved with a precision rarely seen in more productive ecosystems. Many of these lineages trace their origins deep into Earth's past. Their ancestors endured the closure of the Tethys Sea. They persisted through periods of dramatic climatic upheaval. They survived the asteroid impact that marked the end of the Nonavian dinosaurs. They remained as ice sheets, expanded and retreated across continents, and as tectonic forces slowly rearranged the geography of the planet. Their persistence was not built upon resilience to rapid change. It was built upon adaptation to consistency. That distinction matters. An environment that changes little encourages biological refinement. Organisms become increasingly specialized because specialization is rewarded, yet specialization often comes at a cost. The more precisely a species fits its surroundings, the less capable it may be of adjusting when those surroundings shift suddenly. On a tropical reef, disturbance can be severe, but recovery mechanisms are often rapid. Populations reproduce quickly. Larvae disperse widely. Growth can occur over years or decades. In the deep ocean, time moves differently. Growth is measured on longer scales. Reproduction may be infrequent. Colonization of new habitats can require generations. Biological communities that appear quiet are often the result of centuries of gradual accumulation. A disruption that lasts months at the surface may leave traces on the abyssal floor for far longer. The pressures now reaching the deep Indian Ocean arise from several directions at once. Plastic particles descend through the water column and become incorporated into sediments and food webs. Shifts in climate influence circulation patterns, oxygen distribution, and the delivery of organic material from surface waters. Industrial interest increasingly focuses on mineral resources scattered across remote seafloor regions. Each of these changes originates far above the habitats most likely to experience their consequences. The challenge is not simply scientific, it is also philosophical. Humanity now possesses the tools required to enter places that remained inaccessible for nearly all of history. We can map trenches, survey abyssal plains, identify mineral deposits, and send machines into environments once considered unreachable. Technological capability, however, does not automatically provide guidance. The deep Indian Ocean presents a circumstance unlike many others. Knowledge has expanded rapidly, yet vast uncertainty remains. Only a small portion of the seafloor has been mapped in detail. Countless species remain undescribed. Entire habitats have been observed only briefly. Some ecosystems have been visited once and never revisited. And yet decisions are already approaching. Management plans, conservation strategies, exploration programs, and industrial proposals all depend upon judgments made in the present. Those judgments concern landscapes that remain only partially known. They concern organisms whose life histories are still being uncovered. They concern ecological relationships that may take decades to fully understand. The deep ocean offers no direct answers. It simply exists, patient and ancient, carrying the record of millions of years beneath its waters. What it asks, perhaps more than anything else, is humility. Not the humility of inaction, but the humility to recognize that we are still standing at the threshold of a world we have only just begun to encounter, and that the choices made there will echo through places far older than our understanding of them. Long after a research vessel has crossed the horizon, long after sonar echoes fade from computer screens and submersibles return to their hangars, the deepest places of the Indian Ocean remain exactly where they have always been, beyond sunlight, beyond weather, beyond the rhythms that shape life at the surface. It is easy to imagine such depths as empty. Human senses are poorly suited to places without light, familiar landmarks, or visible movement. Yet, throughout this journey, the abyss has revealed itself not as a void but as a vast archive. Layer upon layer of sediment settles onto the seafloor, accumulating so slowly that a few meters of mud can preserve stories spanning millions of years. Tiny shells, mineral grains, fragments of ancient organisms, and traces of long-vanished climates become compressed into a record more enduring than any written history. The rocks themselves hold another archive. Along escarpments hidden beneath thousands of meters of water, exposed layers preserve evidence of continents colliding, separating, and drifting apart across immense spans of time. What appears from the surface to be a single ocean conceals the memory of ancient worlds, recorded in stone and carried silently through geological ages. Elsewhere, far from trenches and fracture zones, hydrothermal vents continue their patient work. Superheated water rises through fractured crust, carrying dissolved minerals from deep within the planet. Around these vents, chemistry and biology meet in ways that have fascinated scientists for decades. The combination of heated water, hydrogen, metal sulfides, and simple carbon compounds resembles conditions that many researchers believe may have contributed to the earliest chapters in the history of life. These vent systems are not merely habitats. They are natural laboratories where Earth still performs processes that may echo events from billions of years ago. Across the abyssal plains, polymetallic nodules rest upon the sediment like scattered stones, yet each one is a monument to time. Metals dissolved within seawater accumulate around tiny nuclei so slowly that growth is measured in millimeters across spans of millions of years. A single nodule contains a chronology almost impossible to grasp, recording the gradual chemistry of an ocean operating on timescales far beyond human experience. Within these environments, live creatures whose existence would once have seemed unimaginable. Hadal snailfish move through trenches under pressures that would destroy most vertebrates. Shrimp clustered around hydrothermal vents cultivate bacterial partners upon their own bodies. Giant single-celled xenophyophores construct intricate structures that shelter entire communities. Transparent eels drift through darkness where no sunlight has penetrated for ages. Every species represents a solution refined through evolution, a response to challenges encountered in environments that remained unknown for nearly all of human history. None of these organisms evolved for our benefit. None were waiting to be discovered. They emerged because the deep ocean provided opportunities and constraints unlike those found anywhere else on Earth. Over millions of years, life responded with extraordinary creativity, producing forms and strategies that continue to surprise the scientists who encounter them. The deepest regions of the Indian Ocean do not ask for admiration or protection. They simply exist. They existed before ships crossed these waters. They existed before humans learned to navigate oceans, before civilizations rose along coastlines, before our species appeared at all. Their future will unfold according to forces both natural and human, shaped by choices made far above waters they will never touch. When the lights of a submersible finally disappear and the long ascent begins, darkness closes once more around the trench. Not an empty darkness, but an ancient one, born during the opening of an ocean more than 180 million years ago. Within it rest records of climate, tectonics, chemistry, and evolution. Within it move creatures still unknown to science. Within it remain landscapes no human eyes have seen. What lies hidden in the deepest part of the Indian Ocean is not a single mystery awaiting discovery. It is a vast accumulation of histories, lives, processes, and possibilities, a world still largely unseen, carrying far more of Earth's story than the illuminated surface above has yet revealed.